we left off talking about Anova. I put a couple other files up there in the in-class data folder just now. We might be using throughout the class today, so we'll take a look at those. I think we actually left off getting through all the examples. So we did the regular kind of Anova. I kind of talked about this two-way, and we looked at the results here, kind of thinking about, was there variation in average income across race and education levels? But it's kind of like, right, we're holding constant whatever the other factor is. So we looked at those results. So I'm just going to show you how we would reproduce some of this stuff in Excel. So first things first, let's make sure you can see this. That would help. Oh, come on. Oh, well, maybe if I hope to send that one out. All right, so I've got two kind of files up here on Canvas. Anova in class, I think this is, I download this. What we worked through. Oh no, this is different. Cool. So let me see. Maybe I just labeled these two different things. Might be the same file. So Anova in class and Anova 2. I think this Anova in class. Let's do the Anova in class one. I think that one's a little bit better set up for what we want to work through today. Okay. So if we're looking at, here, let me see. So this, which one's showing up to you guys? This one's not showing up? Yeah, you're on. Oh, sorry. That would help if I put them in the right section, wouldn't it? All right, I'll give you the second one. So let's go. You have Anova. So let me give you. Okay. Let me give you this guy, this one. So Anova in class, okay? Let me know if that's showing up here. Might have to refresh the browser. Showing up yet? Try switching out of this section. Oh, I just put it on the, I just put it in the files folder. I didn't put it in the in-class data. I can put it there too. You guys starting to show up? Yeah. All right, awesome. I'll put it in here too, just so we've got a couple different places. So let's open that up. Sorry for the delay there. So we'll use this metro cases one. So I had a bunch of this, like I think we used a little bit of it doing that matched pairs. But I had all this county level data on COVID cases and COVID deaths. I specifically looked at October of this last year, just looking at the most recent. And I then went out and you can get vaccination percentages by county as well. Okay. So the percent of the county that's vaccinated. I then kind of grouped all this and looked at counties that were in quartile 1, 2, 3, or 4. So this isn't necessarily that they had a vaccination percent between 0 and 25. It was I took the entire range and like broke it up into the 25th, 50th, 75th percentile. So the first quartile just means like you're in the low end of the distribution, right? So if we're thinking about distributions here, quartile 1 was like all the counties here. Quartile 2 is all the counties here. And then quartiles 3 and 4. Okay? So kind of moving up in quartiles was a higher percent vaccinated. Why is this? Oh, that's a little bit easier to see, yeah. So we're going to look at, and I haven't looked at this data, so I don't know what's going to come out of it. So this could be interesting. But I got the averages kind of number of cases. And I believe I put this in per 1,000 people, just so that numbers weren't like super, super small. So per 100 or per 1,000 people, there's 133 cases in metro areas, metro counties that were in metro areas and had in that first quartile of vaccinated percentages, right? So these are like low vaccinated counties that are in the city. And then you can kind of think about up here, high vaccinated counties, not in the city and in the city. So we just kind of look at the numbers. You can kind of see like, it looks like the non-metro areas actually have, looks like slightly higher number of cases, which is kind of interesting. I think it would actually go reverse, but maybe it's not statistically significant, right? We haven't done this Anova test yet. And then if I look across the quartiles in each one of these rows, notice as I see a higher percent vaccinated, it looks like it's going down, but there's something kind of weird going down here on the lower end of the distribution. So maybe there's like a threshold, right? So initially getting a higher percent vaccinated, these values are going up and then down. It's not changing a lot. But once I can get up to that fourth quartile, I get a large percent of my county vaccinated. Just looking at the numbers, it looks like there's a pretty sharp drop off. Right? But we actually can run some Anova testing. So we'll go to that data analysis tab. Hopefully you didn't wipe your computer, so it's still up there from last class. We'll go here. And what we're going to do is two-way factor without replication. So the with replication is really useful. I'm not going to expect you guys to do it, so I'm not going to walk through examples of it. It's basically taking the original data and not like putting it into this little matrix, right? So this would be like having all of the counties having a variable that identified what quartile they were in, a variable that identified if they were metro or not, and then selecting all of the data. It gets a little bit tricky because I'll show you kind of, you've got all these different options. You have a certain number of rows per sample, so we have to make sure we have a certain number, identify the rows. And if we're dealing with counties, that changes depending on kind of what, how many are metro versus non-metro. We don't have an equal amount. So I'm not going to worry about doing that. So we'll just do the without replication. And I believe they call this a randomized block design. You don't need to know the name, but I think that's what they call it. So we'll select that without replication. Our input data, we'll select, don't select this percent vaccinated label, but we'll select all the other labels as well as the data here. Okay. We'll then tell it that we selected the labels, otherwise it probably gets mad at us. And I'm going to put it on a new worksheet. Okay. So I hit enter here. And then we're going to blow this up a little bit so we can see this a little easier. So I've got a bunch of different output, but really the only thing I'm ever going to kind of expect you to use from this Anova output is going down here where we're looking at the source of variation. So is it cases per 1,000 people? Is there variation across the rows or across the columns, right? We kind of remind ourselves the rows are quartiles, the columns are whether or not they were metro or not. Okay. So we've got two F statistics and we've got their corresponding p-values. So holding constant the column, which our columns were the percent vaccinated. So if I hold constant the percent of the county that's vaccinated, if it's metro or not, right, moving down the rows, the variation in the rows, we see that there is variation in the number of cases from metro versus non-metro areas, but it's only significant at what levels? My p-value is 0.07, 90, and yeah, that's it, right? Because I only reject if that p-value is less than alpha. 0.07 is only going to be less than 1. So with 90% confidence, I can reject that there's no variation across the rows, holding constant the columns. Does that make sense? So, I did find that there's some variation, metro versus non, or rural versus non-rural, but not a super high percent of confidence, right? Only 90. What about, is there variation across the columns holding constant the rows? Well, here, variation across the columns would be, is there variation with the percent of the populace that's vaccinated, holding constant whether or not it's a metro or non-metro county, okay? Well, now if I look at that, it is highly significant, right? 0.004, I can actually reject the null at every one of our benchmark levels, right? 0.004 is less than 0.01, 0.05, and 0.1. So what I'm rejecting is that there's no variation. So with this Anova testing, our null hypothesis is that there's no variation either across the rows or across the columns. We found some evidence that there's variation across the rows. We found strong evidence that there's a lot of variation across the columns holding constant kind of the rows. So a lot of variation in the number of cases a county sees with that percent of their populace that's vaccinated. Right? So, I mean, this is like, I don't know, this is pretty interesting. I don't know, like, I guess for me, when I see like news reports and stuff, especially as COVID's always in the news, like, why don't they just show us this? Like, people, I guess it is like pretty convincing to me, right? I'm looking across every single county that exists, and I can see that, yeah, if the percent vaccinated in the county strongly related to the number of cases, right? So makes sense, right? I can do the exact same thing, but do this with some death data. Once again, I think this was deaths per 1,000 people. So we'll go here, look at the data analysis, two-way factor without replication, select my data, hit OK. So blow this up so we can look at this. So here, and one thing that kind of reminds me, or like the labels I have up here. So I think about, here are my columns and here are my rows, right? So in terms of deaths, what could I say here and what levels could I say it at? So I'm trying to interpret this Anova output. What can I say about the deaths that come from COVID in relation to the variation that exists in either metro versus non-metro or across the quartiles of vaccinated individuals? Yeah.
You can say pretty strongly that there is variation between metro and non-metro areas. So we can also say that there is compelling evidence of variation between deaths as vaccination rates increase.
Compelling evidence. I like that. I like that. Yeah, right. So we've got really low p-values, right? These are less than 0.01. So with 99% confidence, I could say that holding constant the metro status of an area, there is variation. Actually, I went to the wrong data. That there is variation in respect to the percent of the populace that's vaccinated, all right? Or as I move up these quartiles. I could also say that holding constant the percent of the county that's vaccinated, there is significant difference between metro and non-metro areas in terms of the deaths that are occurring. So I'm going to go out on a limb and guess what this death thing, you kind of see here. The non-metro looks like they're all higher. You can just kind of see it in the data, even though that's not, can't say statistically significant there. I'm guessing this has something to do with like people that live out in the country aren't as likely to get to a hospital and aren't as likely to kind of get in when if this things start to take a turn, they might be less likely to be able to get into a hospital quick enough. But I don't know for sure. There's also probably something related to like income, right? Maybe there's income differences across rural, non-rural counties. So we don't have everything, right? It isn't perfect. We've only got 2 factors. There's like probably 50 or 100 different factors, right? We'll eventually get to see how we can control for those today. But this is interesting, right? On its face, this is interesting. And then I can't spell region apparently. So I'll rename that. So I then also broke this down by region. So there's like, you can find the map of how the government identifies different regions of the country. So there's like basically 5. So Pacific is just Alaska and Hawaii. I mean, we could probably have left those out. And then the other ones, it has like different states. It calls the West. It's kind of like the West and the Northwest. You've got the Midwest. You've got the South, which is like Texas all the way over. And then the Northeast, which is like anything above Virginia, I'm pretty sure. Right, so I coded all that up. We've got the average number of cases across these regions and different quartiles, right, of percent vaccinated. So on your homework assignment that I got posted up there yesterday, that individual assignment, the Anova part of it is not individual. You're all using the same data set. But then for the next thing, which we're going to start today and kind of continue on pretty much for the rest of the semester, is linear regression. That part will be using kind of your individual data sets. So that very first question, you'll all be using the same data set, which is basically this, but deaths, right? So we're looking at cases here. Your assignment, you'll kind of look at what's going on with deaths. Right? So I'm going to go run one more Anova. So So really sure that we're okay interpreting these. I'm gonna select my data, hit OK. Gonna blow it up so we can see it. So my rows are now representing different regions of the country, and my columns are representing the kind of different quartiles. Right? So looking at these results, what could I say here? So when it comes to the number of COVID cases, is there variation in respect to the region of the country that people are in? So I'll remind you, we look at the original data, our rows were region, our columns was the percent vaccinated. So if I'm looking at the p-value associated with rows, what's that saying is there variation in respect to the region of the country, holding constant the percent of the county that's vaccinated? Well, here with a p-value of 0.006, I can say I reject that there's no variation. I found strong evidence that there's a lot of variation in the number of cases across these regions. Right? What's interesting, though, is when I hold constant the region of the country, now what's happened to the variation that exists in the number of cases from having a higher percent of your populace vaccinated? Yeah, I can't say that there's any variation. I cannot reject that there's no variation, which is kind of like, it's like almost double negatives here, but like this is where we assume there's no variation. We're failing to reject that, right? P-value is 0.13. Now, maybe with like 85% confidence, we could say that there's some variation holding constant the region of the country with the percent of the populace that's vaccinated. But at the 90, 95, 99%, we actually can't say it once we hold constant this other factor. So it appears that maybe this region of the country is like an important factor when we're looking at kind of the number of COVID cases. And I didn't even run the results for the data I gave you for your assignment. So we'll see what happens when it comes to deaths, right? Now, you know, this kind of makes sense in that like there's a strong tie to like people being outside more, people being cooped up inside. There's some vitamin D things that they've talked about with COVID. So right, it might make sense that it's not just the percent that's vaccinated. It has to do with all these other factors, all these other attributes. Well, I want to control for more than two of them, right? Or at least, you know, start to think about how I can do that. So that's the next thing that we're going to talk about. It's my favorite kind of part of this class. So it takes us the whole semester to kind of get there, but right. I say it's regression review here. But really what we're thinking about is we might want to know the relationship between two variables. Okay. So maybe call this y and x, right? What we're essentially going to do. So I've got my x and my y variable. Maybe this is like years of education and income, right? And I've got this data set with these two columns for these two variables. So I could plot every data point that I have in that data set, do like a scatter plot, right? And then think about, okay, if I could draw a line that best fit that data, what would it look like? So have you guys heard this before? I feel like high school science probably talks about this some to a degree. But right, we're basically taking this data and trying to find a line that best fits this data. Okay. Well, once I have the line drawn, and like we're not going to actually draw it, we're going to talk about the statistical way they come up with this. But if I had that line drawn through the data, it would have some intercept and it would have some slope, right? So y we're going to think of as a function of some other variable x, right? We could then predict y. If I could get values for the intercept and the slope, you could tell me different values for x. Maybe this is, like I said, income and education. So if you tell me a different number of years of education for someone, I can give you a predicted income value. Now, I'm going to be off, right? Like my line, this is all my predictions for what income should be based off of your years of education. But the actual data points, right, I'm going to be a little bit off in my prediction. So we'll come back to this, right? But this is the general idea of what we're doing. So we want to do this thing called linear regression to somehow come up with estimates for what this intercept value and this slope value are. That way we can start to make predictions about what the value of y is going to take on. So we'll call y our dependent variable, right? Y is a function of x. So y depends on x. Okay. So a lot of times I'll say dependent, but I'll also say like the y variable, the dependent variable, the left-hand side variable. Three kind of things referring to the same thing, right? So we're thinking about the dependent, the y, and the left-hand side variable is what depends on x. That makes x our independent variable, right? It is independently changing and causing changes to y. Right? So our x, our independent, or our right-hand side variable, right, are all three different names for kind of that x variable or that independent variable as well. Now, we're going to start out with just one x variable, but eventually we're going to think about income is probably a function of education, maybe your years of experience, maybe this region of the country that you're located in. So we can start to add in several variables. We want to understand how to just do linear regressions with one first, right? And then we'll kind of move on from there. Okay. So regression analysis is going to be the statistical tool that we use to be able to pick up these relationships between our x and y variables. Okay. So I kind of already did this on the slot or on the dot cam here, right? We've kind of got with this line of best fit look like this. My intercept value A would be here, and the slope, excuse me, would be what? I could say here that B is going to be negative, right? I've got this like inverse relationship. As X goes up, my Y values are tend to be falling, or tend to be lower. I could see something like this, which is basically a slope of what? 0, right? As X changes, nothing happens to Y. Right? And then we already did the positive one. Here we would have B be positive. Now, we're going to estimate linear relationships like this. So we're drawing this linear line of best fit. I think we'll eventually get to before the exam. I kind of have to pick and choose my topics in regression. So we'll see if this is one that I find interesting. I usually do. But a lot of times data looks like this. Right? So, data looks like this. So maybe it's not a straight line that would best fit the data, but an actual line that has some curvature to it. In which case we would kind of think about, we might want to look at quadratic terms, right? And so it'll complicate things a bit, but not too much once we get there. We'll then think about, we could have, concave, convex, right? And we'll kind of eventually get to this point, right? But for now, we're going to keep things linear, right, to make it easy. Okay. So I kind of already mentioned this, and I don't know. I think I can do a better job of this by hand, but we'll look at the slides afterwards. So I've got this line of best fit, right? So any X value you tell me, I can plug that value for X in. And if I knew what A and B were, I could come up with a predicted Y value. So any point on this line is what we're going to call Y hat, or a predicted Y value, okay? If I then think about any one observation, my prediction at that X value is going to be off from whatever that observation's actual Y value is, right? So for this value of X, our predicted Y is a little bit off from what the actual Y value was from that actual data point, right? Remember, all these dots here represent different observations in my data set. Okay? So my predictions, I'm going to have some errors, right? So this difference, actually, what do I want? The predictions to low. My error is, yeah. Right, so we're going to call kind of epsilon, this error term, is just the difference between the actual Y value and the predicted Y value, right? Right, it's the error that I was making in my predictions. Okay? So really what we're doing with this line is we're choosing an A and B value such that the predictions that this line makes will produce the smallest amount of error terms. Right? So what we're actually going to do is think about, we're going to try to minimize the sum of all these errors, okay? Right, because across every single observation, actually I should do I equal 1 all the way to the last observation in my data set. I'll take the errors, add them all up, and I want to choose the A and B values that minimize those errors. And not only am I going to do that, I'm actually going to treat this kind of like the variance and over penalize extremely like bad errors. So what's one way I can penalize bad errors? Squaring it. Right? Now it doesn't matter if I'm making a positive or a negative error, right? And the larger my error is, the more I'm going to penalize like kind of this thing that I want to try to reduce or minimize. So from there, I could say, well, I know that my predictions will just be whatever A and B values I come up with. Now I've got something that I can actually take a derivative of, set it equal to 0, and I can take a derivative in respect to A, take a derivative of it in respect to B. That gives me 2 equations, 2 unknowns. I can solve for what those values are. Now, we're not going to do this by hand, but that's the idea behind what we're doing. We're minimizing the sum of our squared error terms, right? And in doing that, we're going to choose the A and B values that minimize that sum of the squared errors. So, yeah, there we go. So like our error term is just, if I rearrange this, right, y minus y hat. I kind of already drew this for you, right? We can think about all these different observations. We're making some errors that are positive, some errors that are negative, but ultimately we just want to minimize the sum of those errors, right? The difference between the actual and the predicted y value squared. Okay. So you would walk through this, take a derivative in respect to A and to B. Those are the 2 variables you're choosing, right? And yeah, 2 equations, 2 unknowns. This is just mathematics, like just some computation. Now, we're never going to do this. Oh, did I repeat the slide? I sure did. Am I going? There we go. So if I actually do that and solve for what A and B are, this would be what I get. So you can walk through the mathematical proof if you want. If you're interested in it, I think I might actually, let me see here. Maybe I don't. I thought I had a link to where, I have a link to the multiple linear regression one. But you can Google search coefficient, what would it be? Coefficient proof, simple linear regression or something, and you could walk through the mathematical proof. But basically you take a derivative in respect to A and B, set them equal to 0, solve for A and B, and this is what you would get. Right? Now, we're never going to do this by hand. In fact, we're never going to even do this in Excel. We're going to have Excel do this behind the scenes. I mean, think about it. If I've got 1,000 observation data set, this would take a while. I mean, I could probably create some columns in Excel where I've got the average X, and take every observation and subtract that from it. Another column where I find the average Y and subtract it from every observation, multiply those 2 values by each other, have that as a separate column. Like I could probably do this, break it down to steps. And in fact, if we have a little bit of time, maybe on Friday, I might do this. I might kind of show you how you could break it down. But Excel will actually do all of it for us behind the scenes. So at this point, why waste time? I mean, it's good to know how to be able to do this, especially if you're like trying to improve your math skills here. But honestly, for most people and for most careers, the value of this is going to be, how do I interpret this result once I get it? Actually being able to compute it isn't near as useful as being able to use it, interpret it to make decisions moving forward. Okay? So are any of you guys econ majors? I forget. You're the only one. So you're the one I like. So no, I'm just kidding. So, but finance and the econ, I would say specifically, any marketing majors, you can set yourself apart a lot if you have a good grasp on linear regression. Accounting, it's somewhat valuable, but I would say it's probably more valuable in kind of econ finance. And then, like I said, marketing would really set yourself apart. Okay. But it's really good to know in anything. I mean, any field you look at, if you have a good grasp on linear regression, you're going to rise to the top of that field. Okay. So once I have Excel do this work for me, and I get this estimate for what the intercept and the slope are, we'll call these coefficient estimates. So the estimates that I come up with after doing all this work using the data set, I'll call this my coefficient estimates. Okay. So we're going to skip this because Excel is going to do all this for us. So I said it might take some time Friday to show you how we would do this by hand. Excuse me, but really we're going to let Excel do this work for us. Where am I on time here? Of course, I can't see the clock. Okay, we got plenty of time. So I'll show you how we use that data analysis tab here before the end of class. But I'll kind of give us an example to set up and think about, once I get these coefficient estimates, how do I interpret them? Right? So I had this data set. It was like a huge survey data set, and people responded with what their income was, and then the number of days that they, I think it says smoke here, but I think it was technically phrased as use marijuana each month. Okay. So, you know, you can kind of see the mean or the median, sorry, was 0. Well, this might be some underreporting here, but right, we have some actual variation that exists in these variables, and we're going to try to pick up what's the relationship between income and marijuana usage. Right? So I run this regression. Really what I'm thinking about here is I want to pick up the relationship between my Y variable, which is income. Right? There's going to be some intercept and some slope, right? Usually you'll see these kind of written a lot of the times as whatever the actual values that Excel spits out at you. These are like your coefficient estimates. Remember how we had P hat? P hat was our sample proportion. A and B hat here would be like our sample coefficients, right? Because they're still coming from a sample data set, right? We're estimating these things with a sample data set. And then here, kind of call this M days, kind of the number of days that they use marijuana each month. Okay. So this is the relationship we're trying to estimate. We run this regression in Excel, or sometimes I'll show you some additional output, which comes from a program called Stata. Have any ever heard of SAS? So it's a lot like SAS. SAS has similar output. I just generally don't use it, so you won't see me show you the SAS output, but it has a very similar format. Okay. So it spits out a ton of stuff at us here. For now, all we're going to focus on is this lower part of the output. Okay? So this constant, sometimes instead of referring to this as the intercept, different programs will call the intercept kind of our constant, right? Because notice when we're predicting income, it's constant in all of our predictions, right? It's our intercept. So that's the estimated value for our intercept. We're also going to have an estimated value for our coefficient on the slope, or the relationship between the number of days using marijuana and income. Okay. So here it's negative, right? Negative 253. Okay. We'll talk about in a second how we interpret that. But before we do that, I want to point out a few more things from this output. Okay. Notice it gives me some test statistics and p-values. So once again, we've got these p-values. And what we're going to start out assuming, and we could do the same thing for the intercept, we just aren't as often kind of interested with it. So our null hypothesis is always going to be that that slope is equal to 0. So if I can get a p-value here, it's basically 0. So if my p-value is less than alpha, it's the same thing as before, right? We have the same rejection decision. So if my p-value is approximately 0, at very high levels of confidence, right, I can reject the null, or said differently, I'm rejecting that there's no relationship between these two variables. I found strong evidence that there is a relationship between these two variables. Okay? So no matter what regression we're looking at, we're always going to use that null hypothesis that the slope is equal to 0. Okay? And then we just use the p-value the same that we have been for all these other examples. Okay? Any questions on that? Okay. what else do I want to say here? So I'm never going to make you like calculate the p-value. It's always going to be just in the output that Excel or that one of these programs is going to give us. Okay. So how do we interpret this slope coefficient? Think about this here. So if I've got, I think it was like negative 253, and I think the intercept was, I already forgot. What was the intercept there? About 32,000. So we'll use those. So what we're saying here is that if I'm trying to predict income, and just thinking about the relationship between income and kind of this marijuana usage, right? Well, I had 32,000 about as my intercept, and then that slope was negative 253. So I could like plug in different values for the number of days, right? 1 through 31 or whatever, right? And come up with predictions, right, for what someone's income is going to be, right? Now, I know that it's going to be a downward sloping line because I have a negative slope, right? The intercept here would be about 32,000. And the way that we interpret this coefficient is, well, think about it this way. Let's say I was thinking about making predictions. This is not drawn to scale, but going from using marijuana 10 days to 11 days every month. Right? Well, that's a 1 unit increase. How much should income fall? Well, if the slope is negative 253, a 1 unit increase should decrease my income prediction by whatever that slope is. So the way that we're always going to interpret these slope coefficients is a 1 unit increase in my X variable causes the predicted Y value to go up or down by whatever my coefficient is. Now, I say up or down because if it was positive, right, I have a positive slope line, it'll go up by that much. If it's negative, it goes down by that much. But it's always for a 1 unit increase in my X variable. Okay. Does that make sense? Any questions on that? So this is your PSA, I guess, for marijuana usage. If you want to make less money here, and then start smoking more every month, right? So, you know, we have to be careful here that we don't interpret this all as causal. We're just picking up evidence here of like correlations, right? Right? Just like with the Anova stuff, we haven't really controlled for anything yet here. Now we eventually will be able to. We'll talk about kind of using multiple linear regression to start including additional variables on the right-hand side. But at least in terms of this simple linear regression, we're really just picking up evidence of the correlation between these two variables. Okay. So there's probably a lot of other things that are factoring in here that we haven't captured yet. Okay. So I kind of already did this interpretation for you. Kind of the general interpretation is just 1 unit increases in your X variable cause the predicted Y variable to go up or down by whatever that slope coefficient is. Okay. And that's always going to be the case. Start hammering that in. Okay. So what about A? Well, how do we interpret the intercept? Well, the intercept is going to be the value of our predicted Y variable if our X variable is equal to 0, right? You think about here, our intercept is the predicted value for Y when our X variable is equal to 0, right? Because then 0 times anything is 0, and we're just left with our intercept. Right? So the intercept interpretation is easy. It's whenever that X variable is equal to 0, that's our predicted Y value. Right? For the interpretation of the coefficient, it's a 1 unit increase in our X variable. It causes the predicted Y to go up or down by whatever that coefficient amount is. Okay. So I already talked a little bit about this. I kind of jumped the gun. We can do left or right tailed tests for these coefficients, right? What we're always going to do is that we're going to assume the coefficient is equal to 0. If you were to take like, I don't even know if they do it in the advanced stats here. Maybe in econometrics, you would start to do this. You can test against other values other than 0. So I might be able to say something like, is the relationship between marijuana days and income greater than 200 or less than 1,000, right? I can use other values. We just typically don't. It introduces a whole variety of additional issues that we usually just want to avoid. And more often than not, we just want to know, is there a relationship between these two variables? Okay. So we're always going to use that assumed true coefficient of 0. Now, I don't write it in as like this assumed gamma 0 here. I mean, what we're always going to be thinking about, where did I write it down? Right, we're just always going to kind of see it written like this. But the correct notation is like gamma 0 here, but we're not going to have to. I'm not going to expect you to know that. But I will expect you to know this. We're always assuming that that slope is equal to 0. Okay. And we use the p-value in the same way that we have been for other hypothesis testing. The steps would all be the same, but we're not doing any of this by hand, so we don't really have to worry about this. But just know that if you wanted to, you could calculate your test statistic, look up critical values, find your p-value. In fact, the equation we have for our test statistic, it's going to follow exactly what we've been doing. We're going to take the statistic we're interested in, right? The prediction or the sample stat that we got. So we'll come up with our sample coefficient, subtract the assumed true value of the coefficient, which I said we're always going to use 0. And then we're going to divide by something called the standard error. Okay. So remember, when we were doing things like one population mean examples, just to kind of give us a reference point. Actually, we were always dividing by the standard deviation of the statistic that we were interested in. We did this with 2 population. We did this even with matched pairs earlier in the week. So it's really the same thing with slope coefficients. We're taking that predicted coefficient value we get, subtracting the assumed true difference of 0. It doesn't really change much. And here, this standard error is basically going to be a measure of the standard deviation or the variation that exists in the data that we use to come up with this statistic. It's just now, it's not like the variance in one variable. It's kind of like the variance that exists between these 2 variables in a way. It's not quite the correct interpretation, but it's a good way to maybe start thinking about it. So, excuse me, what that standard error actually is the kind of sum of my errors squared divided by however many observations I have minus 2. Where that minus 2 comes from, you can kind of think about, we've got 2 variables now. So kind of like back when we were doing sample variances and we did n minus 1, we've got n minus 2 now because we were using 2 different variables to pick up on what that error term was, right? The difference between the actual y and our predicted y. We used our x values to come up with the predicted y, and then we're using our actual y values as the actual y values. So we've got 2 kind of variables we're looking at now. Now, Excel is going to calculate all this for us as well, so we don't have to do this by hand either. So in fact, if we go back and look at that output, right next to your coefficients, you're always going to be given what your standard error is. Okay? So the way that Excel came up with these test statistics is it simply took that coefficient divided by the standard error, right? And then it looked up the test statistics from a student t distribution, and it spit out at you the p-value. Okay? But it's nice that it does all that for us because it's not very much fun to do by hand. Any kind of notice here, like even if you want to check it, right? Take the coefficient divided by the standard error, that would give you your test statistic. Okay. Any questions on anything up to this point? I don't think this is too tough, right? Like this is like easier than some of the other stuff maybe. And it starts to become a lot of interpretation. So, I had one more kind of example here, and since we'll kind of talk through this one, and probably we'll just end class on that, and we'll just do a lot more examples next class. But let's say I have this variable of birth weight, and then I have kind of what we're going to end up talking more about down the road, which is a dummy variable or an indicator variable. So an indicator variable, we treat it exactly the same, but the interpretation becomes a little bit different. Okay, so this smoking variable can only be a 1 or a 0, right? Like the mother either smoked while she was pregnant or she didn't. And we're interested in, okay, how does that impact the birth weight of the child? Okay, so we run this regression. We try to come up with this line of best fit, right? And now what our coefficient interpretation is, so what would a 1 unit increase be? Well, if all we have is a 1, 0 variable or an indicator variable, that 1 unit increase, the way we interpret it is going from the group that would be a 0 to the group that would be a 1. So here, relative to mothers who don't smoke while pregnant, a mother who smokes while pregnant, right, we would see a 1 for that variable. We would predict that that birth weight of that child goes down by 213. I believe this is in grams. Okay. So if we don't have a continuous variable as our X variable, the 1 unit increase just simply becomes going from the 0 group to the 1 group, right? A mother who doesn't smoke while pregnant compared to a mother who does, we would expect birth weights, or our predicted birth weights would be 213 grams lower. Okay. If I wanted to come up with what the test statistic for this was, how would I do that? I would simply take that coefficient of negative 213 and divide it by the standard error of approximately 49. So if I give you some questions on the final to do a test, to calculate a test statistic, like I blank it out like I did here, this is like me trying to give you points, right? I mean, hopefully we'll go through a lot of examples. So it's really just going to become, take that coefficient and divide it by the standard error. Okay. So, any questions on that before we keep going here? So you got that individual assignment up there. On Friday, I'll show you how we actually run these regressions in Excel. That should allow you to complete a couple of the questions on the linear regression. Some of the questions are going to be probably not until like that first week after we get back from Thanksgiving. So I would kind of, as we start to progress through the linear regression stuff, try to chip away at that assignment. I'll also probably get up a final Connect assignment that will have just linear regression problems. Once again, we haven't covered all the material yet, but it would be an assignment that sits out there for a while that you can kind of chip away at as we go along. Okay. All right. I will see you guys on Friday.